So in today's lecture, we're going to talk about the finding heavy hitters and a classic sketch for this called the count-min sketch. So let's recall what the problem is. So you want to find the elements in the stream that occur frequently. So you're seeing a stream of elements, and for example, X appears many times, and you'd like to detect X. So we can think about a few models. And in the streaming literature, there are typically the two models considered are the cache register model, which means it's an increment or essentially an insert only model. You're just seeing objects in a stream and you're keeping a count. The more general model is the turnstile model, where you're actually allowed to both increment and decrement. So you can think of the stream having pairs of the form x comma c, where x is an element and c is a count, which can be negative. And the strict turnstile model, the total counts are always positive. So here's one way to sort of state the problem. You have a frequency vector f, right, which is the final vector of count. So f of I is going to be the total count of the element I. And typically what we're interested in is in finding the k heaviest hitters. So we want to find all elements whose frequency is more than the total. So the one norm of f is the total sum of counts divided by k. And this is called the heavy hitters problem. So find everything which has a sufficiently high count. Now let's just talk about a very basic solution in the cache register model. And in this, suppose we sample a uniform random element in the stream. Then what we can do is we can simply repeat this multiple times. Simply choose many uniform random elements. And if you sort of go through the math, you can essentially find everything. Now one has to be a little careful here. I sort of went through this fairly quickly. So let me just instead say that the simpler guarantee is you just want to report all the elements that appeared sufficiently frequently. And let's just say it's okay to report things that are not so frequent because maybe you'll pre-process them later on. Just to keep the discussion simple. And so if you sample k log k uniform elements, then you can apply Chernoff bounds and union bounds, and you can show that all elements that are sufficiently frequent will appear in your sample. You will also have elements that are somewhat infrequent. Now, there are multiple ways of dealing with this. So suppose you could do multiple passes over the stream. Then in the second pass over the stream, you can go ahead and just compute all these frequencies. So that's one way in which you could resolve this. But if you really want to think of the stream disappears and you cannot go back to access it, then what you would also like to do is to not report any element whose frequency is small. This will actually require more samples. So k log k is not necessarily going to cut it, and you may need to go up to k log n. I don't want to get into that discussion right now. So let's just think that you maybe are allowed a second pass over the stream, which in many cases is acceptable. Or if you really want one pass, then one way to think of it is you just want to be able to detect all the heavy hitters. And it's okay to maybe detect certain elements that are not heavy hitters, because maybe you can deal with them later. If you really wanted to get both these guarantees, you may have to increase the number of samples.
Wait, but
yes.
If the stream disappears and you can't go back, then doesn't that also break our idea of how to sample uniformly at random?
No, so the amazing thing about reservoir sampling is that it actually allows you to sample even when the stream disappears. So reservoir sampling is this mechanism where you can sample a random element from the stream even if whatever has passed has disappeared. Or do you mean the other way around? Like if you can go back to the stream, then it's much easier.
Well, no, I mean like if we wanted to sample two elements uniformly at random from the stream, then we'd have to go back.
No, so actually, so if you look at reservoir sampling, so okay, here's the mechanism for reservoir sampling, right? So on seeing the tth element of the stream with probability 1 over t, you replace the stored element by what you see. You can do this process for multiple independent stored elements.
Right. Yeah.
And this will give you k sample, like how many ever samples you need.
Sure.
So this is how you, in one pass, you could then sample from the stream.
Okay, makes sense.
Yeah. And I don't want to get into the reservoir sampling math, which we did last time. I do want to mention that there is a deterministic solution for this problem called the Mr. algorithm, which in k log n bits actually will report the top k elements. So you might think, well, you already have a deterministic solution, so why bother? Like, I mean, what's left to do? And there are really two issues with both Mr. Grace and the reservoir sampling approach. Hang on, let me just move this down a bit. Just want to fix that. So there are really two primary issues here. Two issues with the reservoir sampling and Mr. Grace. So the first, and I'd say is the primary issue, is that the algorithms are not what we will call sketches. So what is a sketch? A sketch is an easily combinable summary of the stream. So, or composable. So what this means that given streams A1 and A2, the sketch of A1 concatenated with A2, so this is just concatenation, can be easily computed from the sketch of A1 and the sketch of A2. So the deterministic Mr. Grace algorithm is definitely not a sketch. For the reservoir sampling, you could potentially try to combine them by storing the lengths of the sketches. But even then, it becomes a little messy. But you could imagine that in one portion you got a uniform random element, in the second portion you got a uniform random element, and you could potentially try to combine them. But the deterministic solutions are not sketches. And it's also nice to have methods that can easily have an interpretation as a sketch or a summary of the stream. So this is sort of the first point. And the second point, which is also important, is that the algorithms work in the cache register model, not the turnstile model. So, Mr. Grace, which of course I have not described, and the reservoir sampling do not handle deletions. Yes?
If you could just briefly describe the difference between cache register model and turnstile model.
Sure. So cache register model means that you only have increments. So you're just seeing a stream of items go by. In a turnstile model, each item also comes with a count, and the count could also be negative. So you could imagine that you're seeing element inserts and element deletions. So that's the distinction.
Okay, thank you.
Professor, another question. You talked about summary, right? Could you please elaborate? Like, is it just statistical summary, like mean variance, or is this more?
So, okay, so this is, I guess it's not, I have not formally defined it, but, so okay, let me draw a picture which may be what I mean by a sketch. So here's your stream, right? And so here's your algorithm, and your algorithm is sort of passing through the stream, and at the end of it, it has stored, there's something stored in its memory, right? That's basically what the streaming algorithm is. Now let's just say you have another stream, okay, and then you run the same algorithm, and it's going to have something in its memory as well. So let's call this stream A1 and A2. Now what you have stored in the memory you can think of as some kind of summary of whatever has been seen in the stream. What you would like to do, so I'm going to call this memory 1 and memory 2. This is what is stored in the memory after the algorithm passes through the stream A1. This is a separate instantiation of the algorithm passing through A2. Now suppose you combine these streams. So here's A1 and A2, and you run the algorithm. What its memory is going, this is going to have something else, which I'll call memory 3. With a sketch, you can easily combine these to compute this. So the question is, can you actually, suppose you took your stream, you broke it into two parts, and you fed it to independent algorithms. So it's almost like, can you distribute the computation? So if you have a sketch, then you can essentially distribute the computation. So this memory 3 can be computed from memory 1 and memory 2. That's what it means to be a sketch. Does that make sense?
Yeah, thanks.
Yeah, so are there any questions about what a sketch means?
Is it intended that this, are we only providing this guarantee for like pairwise combining sketches, or should you be able to combine any number of sketches?
You should be, but if you can do it pairwise, then typically you can just, you can just iterate through all of them, if that makes sense. You'll see that whatever we do, is easily generalizable to combining multiple streams, but if you can combine two streams, then you can do multiple, right? Because you combine the first two, then that with the next, and so on and so forth.
I'm just kind of confused how you can deal with, say, like, you have a frequent element in one stream and a frequent element in the other stream, and then some infrequent elements in each stream, and the infrequent elements, their sum ends up being more frequent than...
Yeah, that's an interesting question. That's exactly what you need, which is why deterministic solutions actually will not work. But if you think about the reservoir sampling approach, that might work, because if you sample random elements here and random elements here, they might not be frequent enough within this and frequent enough within this, but the sum is going to be frequent enough. Does that make sense?
Yeah, I mean, I'll see one.
Yeah, so you'll see the sketch that I'm going to present, and hopefully that will make it clear. Okay, so I'm going to talk about a classic result. It's not the first one, but it's actually a very, very nice algorithm by Kormod and Muthukrishnan in 2005, and this is called the count min sketch. And this is it's reminiscent of Bloom filters, although I haven't taught Bloom filters, but the idea is kind of similar. Okay, so the idea is that we have T independent hash functions. So for now, let's think, we're in this realistic model where we can just come up with more and more hash functions. And you could do it by just seeding a cryptographic hash function with different seeds, for example. So we have T hash functions, and I'll index them by S. So S is going to be between 1 and T. So S is an index of a hash function. And it's going to map the universe. It's going to map our elements to some universe of size k. Okay, so that's what we're going to maintain. Now the data structure. So the count-min sketch is really a data structure, and the data structure is updated, when you see a new element or a new count. So the data structure is actually going to be a table, and it's going to be a T cross K matrix. That's what we're going to store of counts. So the sth column here, this really corresponds to HS. So these columns, I'm sorry, the sth row. So all the rows you'll see are basically going to be independent. Okay. So to update, so on seeing, now we think of the turnstile model, an element I, comma C. So I is the element, C was the count. What we'll do is for all S at most T, okay, so I'm going to refer to this matrix as C. That's the array. So for all S, I'm going to go to the sth row, and then I'm essentially going to map I to whatever HS of I does. So maybe I'll write it as follows. So it's like I'm going to place it into a bucket. I have to update a count. Now let's just say K was equal to N. Then what I could do is I'm just maintaining all the counts explicitly, right? If I set K to be equal to N, then I can just maintain all the counts explicitly. T could be equal to 1. So this is just sort of the trivial data structure. I'm going to compress here, right? So K is going to be much smaller. So I need a hash function that is going to hash my elements or map my elements to a smaller universe. Now I just place that element, the ith element, in the appropriate bucket. So I'm just going to sort of increment that by C. Right? So this is the update. Okay, so does the update make sense? On seeing an element with a count, so I'm describing it naturally sort of in the turnstile model. You could get an increment or a decrement. It doesn't matter. You basically pick up the sth row. You go in that row. You look at HS of I, which means you apply the hash function to the element I. This gives you some bucket you can think of, which is basically an element in this two-dimensional array, and then you go and increment by that count or decrement appropriately. So any questions about what the count-min sketch is?
So on collisions, it would increment probably something else.
Exactly. So the problem is to understand the collisions.
Okay.
Right? I mean, exactly. I mean, you've pointed out the issue, which is like we have to understand what happens on collisions. And the question really is, what should we set K to be so that we can kind of control the collision count?
Why is it called the count-min sketch?
You'll see. Okay, I haven't told you exactly. So this is the count part. I haven't told you the min part. Okay, so now let's talk about output. So actually, at any point in the algorithm, we can just say for any j in n, our estimate for the jth count is going to be the min over all less than t of CS HS of j. So let me go back to the picture. I think it will make much more sense with the picture. So let's say that now, I've ended, the stream is ended, and I'm trying to find out the heavy hitters, or maybe I'm just trying to get an estimate for the count of the jth element. For the count of the jth element, I want an estimate. So what I'm going to do is, I'm going to see where j maps to. So it maps to basically some column, right? This is the column corresponding to HS of j. And I look at the minimum count amongst all of these, the minimum count, and just output that. That is the estimate for f hat of j. Now you might say there seems to be something fishy here, because there are obviously multiple elements that are going to collide, and they're going to give you the same estimate. So what kind of guarantee can we give? So the guarantee that we will provide, that we would like to say, actually let's first talk about storage. So the storage clearly is k times t times log m. Let's assume that we have hash functions available. It's k times t plus log m, in sort of the realistic model. But if you really wanted to deal with, if you did not want to assume the existence of hash functions, you would have to add another t log n, in theory, to generate sort of t-wise independent hash functions. I should say to generate t two universal hash functions. So I should say t independent two universal hash functions. Right? So this is to generate t. I should put the independent two universal hash functions. You'll use t log n bits. But if you already assume you have the hash functions, then you can just look at this. So a lot of these results you'll see are often decomposed into two terms. One is what it takes to store the hash functions, and you can think of it as the main term, although it might actually be asymptotically smaller. But the main term is often, what you need on top of the hash functions, which is sort of the real data structure. Okay, so this is the storage. What is the guarantee that I want?
Quick question.
Yes.
So when you, in the picture, you drew like a column to represent what you're taking the min over. Am I correct in thinking that it might actually be all over because you're taking hashes of that element?
I'm sorry, say that again?
Sorry, so you are taking the min over all the rows, but you have different hash functions for each row, so it's probably not all going to be in the same column.
Yeah, I agree with that.
Sorry, you're right. This is this is a bad picture. Sorry, I take that back. No, I made a mistake here. So you're right. It's not the same column. So I should draw this picture better. You're absolutely right. Sorry, I misspoke here. So here is T. Here is K, and so we will look at Hj H1. We look at H1 of J, H2 of J, H3 of J, up to H T of J. So that's like it's a bunch of different entries here, right? And I just look at the minimum of all of those. There's one entry in each column.
Okay, so can you please pull up the sheet of paper? Thank you.
Right, my apologies. I'm sorry, I misspoke. That's what happens when I say something that I haven't written down before. So you're right. So you're absolutely right. So essentially, the count min sketch says you look at, for every s less than t, you look at hs of j. So you're looking at h1 of j, the h1 of j entry here, the h2j entry here, the h3j, so on and so forth. These are all different positions in the array, and you just take the min of all of those.
Question.
Yeah.
So this matrix actually store the count of each I, right?
It stores the count of each element of the hash function, each element in the range of the hash function.
Okay.
Okay, so let's walk over this count again, right? But let's not use my bad picture there. So what this is saying is that each row corresponds to a different hash function. Each row corresponds to a different hash function. For each row, you're just maintaining counts corresponding to the range of that hash function. Right? Because this is k. So when you see the element j, you are going to increment. Let's just say we're in the cache register model to keep things simple. When you see j, you're simply going to increment these places. When you see another element I, you're going to increment a bunch of other places. Now, the problem was collisions. But what you expect is if you take two elements I and j, they're not going to collide everywhere. And because somehow if you can control the number of collisions, which you expect will happen in a hash function, will spread it out uniformly, you expect that this count is going to be, will be sort of accurate. At least you hope, and that's what the analysis will show. Okay, so any questions? Does the algorithm make sense and the output make sense? We'll talk about the analysis. But the algorithm is simply it's maintaining a matrix of counts. Each row of counts corresponds to a different hash function. On seeing an element, it's going to compute the hash value of those elements for each of the t hash functions and increment the corresponding counts. When it has to finally give an output, it looks at those positions and outputs the minimum. So one thing that should be relatively straightforward is that for all s greater than t, s at most t, Cs hs of j is greater than or equal to the true frequency. And that's because every time you see j, you're going to increment that position. There may be other elements that also increment that position, but that will keep it as an upper bound. This happens in the turnstile model. In the turnstile model.
Wait, in the turnstile model, can't we decrement?
I'm sorry, no, okay, today's not a good day. I mean, in the cache register model.
Okay, thank you.
In the cache register model. Because in the cache register model, all you see are increments. And therefore, everything is only going to increment. Collisions are only going to increment the counts. And therefore, you have this claim. Okay, so this is an exercise. And that's why you know that the min which is equal to the estimate, is going to be greater than the true value. And the question is, how much is the deviation? How much is fj minus fj hat? Okay, just zoom out a bit, have some more space. All right, so does that make sense? Any questions? All right, and so what is the guarantee that we are going to show? We'll show that, or I'll say when t is, so I'll say that when t is at least actually log 1 over delta, and so when t is at least log 1 over delta, f hat j minus f hat I, what you want to will show that this is going to be essentially, let me write this out, divided by k. Now, formally speaking, what I mean is this will happen with probability at least 1 minus delta. Okay, and I have to be careful with the quantification here. So I'll say fix any j. So you fix an element. If t is greater than log 1 over delta, then the guarantee is that the approximation is going to be correct essentially up to, and we call this m over k. So for all the heavy hitters, we sort of expect to get a reasonable approximation. Okay, so
what is k again?
So k is just a parameter here. So for any choice of k, you get this guarantee. So, and remember, k is sort of saying like you wanted the top k heavy hitters. And so that's what the k is. And what this algorithm or the guarantee says is you will set this to be how many heavy hitters you want, like times some constant factor. You will set this to be t to be the log of the confidence you want, or the log of 1 over delta, and you get such a guarantee.
Okay.
So the storage is essentially O of k log 1 over delta log m. This is assuming hash function in the realistic model. Right, so it's k log 1 over delta log m. And if you really wanted to have such a guarantee hold for all vertices, then you would have to make this be log n, and then you would get, you would basically get k log n log m, and then you could apply union bounds over all the elements. Okay, this is the guarantee that I'm going to show you. Okay. So let xj, the random variable, be equal to f hat j minus fj. This is the overestimate of the element j. And we're trying to bound what this is going to be. Okay, so now let's write out this other random variable. This is the indicator. Now I'm going to basically put that over there, saying this is the indicator for hs of I being equal to hs of j. So xjs is the overestimate of element j. But let me now create what is the overestimate for each hash function. So this is going to be CS of HS of J minus the truth. So this is the overestimate of the sth hash function. And remember that xj is just going to be the min over all s of xj of s. Now we can write xj of s as the summation over all I in n, and I not equal to j, so this is the overestimate, is going to be that if that element j, I collided with j, times whatever the count of that I is going to be. Okay, does this make sense? The overestimate in the jth function is obtained because of collision. So you say for every other element, if it collided, then it would increment this cell, which is the cell corresponding, the bucket corresponding to j. It is going to increment that by fi as well, and this is going to be the overestimate. Okay, any questions about that? Is that clear? All right. So let's do our usual. Let's compute the expectation. And what we get is this, the expected value is going to be fj times the expectation of yij of s. This is linearity of expectation. This is linearity of expectation. Now let's look at what is this. This is simply the probability that hs of I is equal to hs of j, and this is exactly 1 over k because it's a 2 universal family, right? All I need is 2 universality. I don't need anything more, because I know that conditioned on the choice of hs of j, the probability that hs of I has that same value is just 1 over k. And so what this gives me is at most, because I can even get rid of the I not equal to j. I'll just say that this is at most 1 over k times summation of fi, which is exactly equal to the total count divided by k. So the expected overcount is precisely the total sum of counts divided by k. So this is the sort of the magic of, this is one part of the magic, I guess. And the second part is going to show you that the min is the right thing to do. So it says the expected overcount is sort of exactly the error that you're looking for. Okay, questions? All right. Now we'll just apply Markov. So by the Markov bound, the probability that xj of s is more than, let's say, 2 times that deviation is at most a half. Right? And so just to be clear, this is probability over the sth hash function. So the probability of just being 2 times the expectation is at most a half. Just use the Markov bound.
Question.
Yes.
So you say the expectation of xj equals to the sum of fj multiply expectation of yij, but above that you said it is fi multiply with yij.
I'm sorry, this was it. Thank you. It's Fi.
Yeah.
And just to be clear, at this point I use linearity of expectation. Yeah, sorry about that. Yes, today is definitely not my day. So so it's Fi, and by linearity of expectation, I get this bound. I apply the Markov bound, so the probability that the overestimate is more than 2 times essentially m over k is at most a half. And this is for the sth hash function.
Isn't it also true that the probability that it's greater than 1 times the expectation less than a half?
No, the probability that it's, you mean the probability that it's more than the expectation?
Yeah.
No, that's not necessarily true, right? What if the random variable essentially always took its expectation?
Right, yeah.
It's not a symmetric random variable, right? Rather, it's not symmetric around its expectation. All right. Any questions?
Again, sorry. So do we assume that for every HSI equals to HSJ, the probability is k 1 over k?
You mean, do we assume this to be true for all S?
For all I and j.
For all I not equal to j, yes.
Okay.
Because this is a 2 universal, family of hash functions. So essentially what it says is you have pairwise independence on the values of the hash function. So if you take 2 different elements, the probability that they map to the same thing is just 1 over k. It's as if it's random.
Also for all S, right?
This is also true for all S, and that is independence, which we are going to use shortly. This is only 2 universality. This is why only pairwise. For a specific hash function, you only get pairwise independence. Interestingly, that's all you need here. You don't need anything stronger, which is really nice.
Thank you.
Any other questions? Okay. So I'll continue. So by Markov we have this guarantee. So this is the overestimate for the sth hash function. Now we simply ask, what is the probability that all overestimates or are more than 2 times f by k. And now this is where we use independence of the hash functions. Not of each individual hash function, of the hash functions amongst themselves, of the independence of h1, h2 up to ht. We can write this as the product of s most t of the probability that xj of s is more than 2 times the L1 norm of f divided by k, the sum of counts, and this is at most 1 divided by 2 to the t. So it decreases exponentially in the number of hash functions that you choose. So if we set t to be the ceiling of log 1 over delta, then this probability is at most delta. And then that gives you the analysis. So that means that, so we fixed j, probability that the final estimate is more than, which is the true count, plus 2 times f1 divided by k is at most delta. And the storage let's recall, was O of k log 1 over delta log m bits. Remember, this is giving it for a fixed j. So you have to be a little careful, like you don't get this guarantee for all j's simultaneously. Right? You fix a j and then you get this guarantee. Okay, so any questions on that? So that is basically the end of the analysis of the count min sketch. I will mention that in the turnstile model, we can use the count median sketch. So which is you output the median of CS HS of j. The analysis is, is a little more involved. You have to use some kind of Chernoff bound. But essentially this also works. The analysis, the idea is fairly similar. Instead of the overestimate, what you do is you count the deviation, and you'll see that the expected deviation is exactly going to be the same. It's going to behave in pretty much the same way. And since the expected deviation behaves in the same way, then you can essentially say that the median of independent deviations, is going to behave as expected. And then that deals with the turnstile model very cleanly, in pretty much the same way.
So to be clear, could we also use the count median sketch for this model?
You can also use the count median sketch in this model, but in practice, count min is going to be better because you might as well just take the minimum estimate. I mean, it makes sense to take the minimum estimate because you know that, because of, so where do I have this written? Because of this claim, in practice, you are going to get the minimum error by choosing the minimum estimate, but you can take the median as well.
Wait, so we wanted to find all the elements with frequency more than m over k, right?
We wanted to find the elements, that's right.
So it seems like this is not a very good, like there might be elements that are very infrequent,
Well, if you set, so you have to play with this a bit, but let's just say you wanted to find the top k heavy hitters. Instead of putting k here, you could put something like 10 times k. So then the deviations are all going to be at most f divided by 5 times k.
Yeah.
And then you look at the estimates that are more than, say, f divided by 2 times k. And then that will give you all the large elements. You have to be a little careful with making sure that you get the errors, the union bound errors working out. Right? That requires some care. But you could always set delta to be 1 over n, and then you'd be done. Then you would get this estimate for all elements simultaneously, and then so think of it as you rescale k by a constant factor.
Yeah.
So it's a somewhat abusive notation on my part to call that k. Maybe I should have called it k prime, and then you say you set k prime to be like 10 times k.
Sure.
But the nice thing, of course, is this is this very nice sketch, because once you get the sketch, you can combine two sketches really easily. You basically just add them up. Right? If you have two sketches, you'll just add the sketches up. Like you have one matrix, you have another matrix, you'll just add the matrices together. And that's it. Right? So combining the sketches is just adding matrices. is basically just adding the count matrices. So any further questions on the count min sketch? I should say there is also something called the count sketch, which gives a stronger guarantee at the cost of more storage and more complex algorithm. But I think the count min sketch is really, it's very elegant, it's very easy to describe, and it gives this really nice guarantee. And also, surprisingly, you only need a two universal family of hash functions. You don't even need full independence. You only need the independence across the different hash functions. But that's easy enough to guarantee.
Is there a significant improvement if we do assume full independence? Because it doesn't seem like...
No, it doesn't buy you anything.
Yeah, because that step doesn't actually translate into it.
Well, okay, so let me step back and say that if you assume full independence, you see, you could get yourself more, right? Right now, all we do is we just do Markov. So in this analysis, it doesn't buy you anything.
Okay, yeah.
But if you had full independence, then xj of s would be maybe much better concentrated around its average. Right? If you had full independence, then you would have, each of these would be fully independent. This is a sum of independent random variables which could behave much better. And so under certain settings, what would happen is maybe this error would be much smaller. The benefit of this error being much smaller is then maybe you could choose t to be even smaller. So indeed, these considerations are, if you were to actually tune this data structure in practice, and you wanted to find out, what is the right size to keep, then assuming independence may be beneficial. In the worst case, it probably won't, because in the worst case, what could happen is that if you look at the sum of random variables, they're weighted by fi. So a few of the FIs could dominate the sum, in which case then you're not going to do much better than Markov. So it depends on the parameter space, but you can probably squeeze out more in the constants if you assumed full independence. The count-min sketch has been implemented and used in practice. So, I think these considerations are of use. I don't know if I've seen specific results on this, but it seems like an interesting direction, although people may have worked on this.
That makes sense. Thank you.
Okay, any questions? Okay, if not, then what I'd like to spend, I guess, the next 45 minutes or so, or maybe even less, the next half an hour to 40 minutes, is on the last topic in streaming, an extremely important problem. So we discussed two problems so far. One is, counting the number of distinct elements. The second is to find heavy hitters. And our third problem, which is sort of a classic in this literature, is what's called estimating frequency moments. And I'm going to use this capital FK. So a lot of this notation and a significant part of the math is borrowed from Amit Chakrabarty's notes, which I've posted on the website. Which is exactly what you expect. The kth moment is simply the sums of the kth powers of the counts in vector. I'm just going to use the vector notation over here just to keep things a little clearer. It's just the kth power of the kth norm. Now the second moment F2 is of special interest. It sort of pops up in many applications. Let me just give you an example which you can see. So if we are streaming through the tuples of a database, then F2 is the size of the self-join, where Fj is the number of tuples with value j of the join attribute. Right, so Fj, which is the sums of squares of the frequency counts, is of special interest because if you were to think of streaming through the tuples of a large database and you're doing a self-join on a particular attribute, then that attribute takes a bunch of values which you could think of as being going from 1 to n. And Fj is basically the number of tuples with the value j on that join attribute. And Fj squared is basically, the number of new tuples you will get when you do a self-join. And so the sum of, in this case, Fi squared or Fj squared, the second moment, gives you the size of the self-join, which is sort of a very important quantity to know of when you're dealing with databases. So this is an example of the second where the second moment would be useful.
What is a self-join?
So the self-join is so what you can think of is if you have two tuples that share the value of a particular attribute, then you sort of combine those two tuples on that attribute to get a bigger tuple with all the others. This is something that comes up in databases. So maybe the easiest way to think of it is if you have a graph and you think of your tuples as just edges. The self-join is the number of paths of length 2. Right? So in this case, the self-join is the number of paths of length 2. So you can even think of it just for graphs. This actually comes up a lot, which is you stream through the edges of a graph, and you like to find out how many edges have length 2. How many paths of length 2 exist in this graph, sorry. Definitely today is not my day. So how many paths of length 2 in the graph? That would be the second frequency moment when you're streaming through the edges. Okay, any questions on what the problem is? So this problem and the algorithms that I'm going to discuss were introduced in a seminal paper by Alon, Matthias, and Segedi in '99, who gave streaming algorithms for estimating the frequency moments. And let me talk about two of their results, and in the end, towards the end, I'm going to actually show you their most celebrated result. I may not do all the math in gory detail, but hopefully show you enough that it should be clear how to work out the rest of the calculations. So let's start with the basic algorithm. Our basic algorithm to estimate Fk. Indeed, we'll think of k is greater than 0. Again, F0 is of interest as well, because F0 is the number of distinct elements. Maybe I should put that up. So F0 is the number of distinct elements. F1 is the sum of elements, the total number. And so the other moments tell you various other aspects of the counts. So the idea is actually quite simple, and it's again like let's start by some kind of reservoir sampling type approach. So suppose we could sample I proportional to f sub I, and we could try to use reservoir sampling to do this. But let's ignore the reservoir sampling aspect aside, because that's going to introduce a technicality. Suppose we could just sample an I proportional to Fi before the stream. And then we could simply just output f of I to the k minus 1. So the expected output times m. And I'm just going to use m for f1, which is a 1 norm, because just to prevent carrying around the norms. So what is the expected value of the output? So it's a sum over all I going from 1 to n, f of I divided by f1, the sum of all counts, which is m, times m, times f of I times k minus 1, which is this value here. Sorry, I switched the position of the m. The m and m will cancel out, and this gives you exactly f of k. So this is the idea. Sample I proportional to fi, and then output f of I to the power k minus 1. This is a really neat idea, by the way. So it's something that I would, it's something to remember, that when you're trying to estimate the moment, if you can actually, in a distribution, and so if you can sample an element proportional, if you could sample I proportional to its frequency, then you could output f of I to the k minus 1. Now clearly it's not obvious how to implement this in the streaming setting. Potentially you can sample something proportional to f of I using reservoir sampling, but how do you actually get f of I? So the problem is, by reservoir sampling, we get a random element at the end of the stream. So we cannot compute f of I a priori. So on sampling I, we can only count subsequent occurrences of I. Now what this means is, here's your stream, right? And maybe I appears here, and I appears here, and maybe I appears repeatedly in this block, so on and so forth. So let's say you reservoir sampling decided to sample I at this point. So here the reservoir actually has I. It can only count how many occurrences of I happen afterwards, subsequent occurrences of I. And it's not clear it's going to get f of I. Suppose we just plugged in the number of subsequent occurrences, just to see what we're going to get. Just to understand what the math is. So conditioned on sampling I, we want the output to be m times f of I to the k minus 1, conditioned on sampling I. But suppose you only used the subsequent occurrences. not the true number of occurrences. Let's just see what we're going to get and see if we can fix this bias. And this is often a way in which you design streaming or even randomized algorithms. You're going to say, okay, so I start with an ideal algorithm. This is the ideal algorithm. And now you have these two steps. One is to sample an I proportional to Fi. The other is to output Fi to the k minus 1. And you look at these two steps and you say, okay, so how can I implement them in the streaming setting? The first one I know I can do reservoir sampling. But if I do reservoir sampling, I need to get f of I. I don't know how to get f of I. I can only get the number of subsequent occurrences. And so I'm going to just start by doing the math with whatever I can count, and then you'll see how to fix this problem. The very clever fix. Suppose we output r to the k minus 1, where r is the number of subsequent occurrences. So think of your reservoir as going through this, and your reservoir is at some point, going to decide to keep I. And let's just say, suppose it decided to keep I and stick with I for the rest of the stream. At that point, you can now start counting all the number of subsequent occurrences, and you could just output r to the k minus 1, where r is the number of subsequent occurrences. Ideally, you want to count all occurrences. And I'll say m times that. Let's go ahead and see what we get. So conditioned on sampling I, we want to get Fi to the k minus 1 times m. Let's see what the expectation of this quantity is. So we get, again, conditioned on sampling I. What we'll get is, we'll get 1 divided by f of I, summation of, so that instead let me use, let me not use j here, let me use some other, let me use s going from 1 to Fi. So this is just saying, now here is my stream. There are a total of, and let's just think of turnstile for now to keep it simple. I'm sorry, let's just think of cache register model. Let's just think of cache register model here. So I'm just doing the cache register model here. So there were Fi occurrences. I picked one of these at random because I'm conditioning on sampling I. Reservoir sampling is going to pick one of these at random, uniformly at random. That's the 1 divided by Fi. So I could pick the first occurrence, the second occurrence, so on and so forth. Or I could, let me count S backwards. So I could pick the last, the second last, the third last, the fourth last. So if I pick the last occurrence, I'm going to say my count was just 1. If I pick the second last, my count is going to be 2, so on and so forth. So I get S to the k minus 1. And clearly, this is not Fi to the k minus 1, but maybe it's somewhere around there, right? Because if you just sort of say approximately what is it going to be, right? It's approximately, it looks something like Fi to the k divided by k and times 1 over Fi, and so it seems like it's approximately going to be Fi to the k minus 1 divided by k. This is an approximation, but there's a neat trick. So if we can somehow fix this to get an unbiased estimate, what we could do is, maybe could we, instead of outputting S to the k minus 1, which is, can we output something else to fix this problem? And this is exactly the basic Ams algorithm. The basic Ams algorithm is to run reservoir sampling keep track of the number of subsequent occurrences of stored element. And we'll call this R. And finally what we're going to do is just output m times r to the k minus 1 minus r minus 1. So r to the k minus r minus 1 to the k. And this is actually approximately r to the k minus 1. If you write out the binomial expansion, see it's approximately r to the k minus 1 with a little bit of a fix. And that fix is going to fix this problem. Hopefully this makes sense. Now, and when you do reservoir sampling, your sample might change. And if you sample your change, then you just forget about whatever you saw so far. So now it just starts afresh. And then you track subsequent occurrences of the stored element. Okay, so does this make sense? Questions?
Can you go over the fix again?
I have not explained the fix is right here. This is the algorithm. I'll show you how the fix works. So let's look at what is the expected value of the output. So the expected value is, well, I'm going to sum I going from 1 to n. The expectation of the output conditioned on I being the reservoir sample times the probability that I is the reservoir sample. Okay, so I'm just going to, by reservoir sampling, this we know is exactly Fi divided by n. So I'll get a 1 over m here. I going from 1 to n, f of I, times the expected output conditioned and I being a reservoir sample. Okay, now let me work this out. So it's f of I times, now there are f of I different positions, right? And if I output from here, it's going to be, the choice of R is going to be either 1 or 2 or 3 all the way up to f of I. So the R can take any of these values, but it takes all of those values with the same probability. And therefore, I can write this out as f of I times the sum over R going from 1 to f of I. Each choice occurs with probability f of I times R to the k minus R minus 1 to the k, and times m. Right? There is an m because the output is m times R to the k minus R minus 1 to the k. Now, of course, these things all cancel out. So I have I going from 1 to n, summation of R going from 1 to f of I of R to the. But this is a telescoping sum, right? I mean, this is, so if we write this out, what do you get? You get 1 to the k minus 0 to the k plus 2 to the k minus 1 to the k plus 3 to the k minus 2 to the k, going all the way up to f of I to the k minus f of I minus 1 to the k. This cancels out with that, this cancels out with that, so on and so forth, and what you're left with is exactly f of I to the k, which is equal to fk. It's beautiful. So the expectation of the output with this fix is exactly f of k. Any questions? Okay. Now,
how they came up with it?
Sorry?
Do you know how they came up with it?
My guess is you start from this math. You say, well, this is approximately that. And then if you say, how do you fix this? Well, you could make it be k times sk minus 1, s to the k minus 1. And that's approximately what this is. If you open this up, you'll basically get like the first term, the r to the k is going to cancel out, and then you'll get k times r to the k minus 1. So it's kind of approximately the same thing. And then it requires a bit of a leap to get to the telescoping sum. My hunch is they would have started, I don't know, like if you had asked me how would I get to this, probably I would have started with this. Because I know how to count this, and then go over this math and say, oh, is there some way I can fix this bias? And then you come up with a clever fix. Of course, this only gives the expectation. There is a theorem that says the variance of the output is at most n to the 1 minus 1 over k times the expectation of the output squared. Unfortunately, I don't have time to do this. But, when you this requires some amount of algebra, and eventually this yields and so I'll say it's a big O of tilde. There are some log factors that I'm hiding, but it's n to the 1 minus 1 over k divided by epsilon square space algorithm. I mean, each individual estimator just takes log n or log m storage, and then you have to repeat this n to the 1 minus 1 over k over epsilon square times to get some kind of convergence. And that comes from the variance bound. And just to say, for k equals 2, this is O tilde of root n divided by epsilon square, which you think about it, we've seen this bound before. And this is like the birthday paradox. And this should now be, in some sense, no surprise, given that the second moment, if you look at what the second moment is, which is this f of I squared, this is like this collision probability. Like if you take two independent elements, what you get is the collision probability. And therefore the second moment is related to the birthday paradox collision probability, and you can actually get an alternate algorithm for this using the birthday paradox as well. Like you could sample two elements, you could sample a bunch of elements and then count the number of pairwise collisions. That also works. Although this algorithm can be converted to the turnstile model with some effort. And a natural question is this optimal? And surprisingly, the answer is no. You can beat this. And so the classic AMS, whenever you hear references to the Alon-Matthijs-Szegedy algorithm, often, just get a new pen, what they're talking about is an O of log n over epsilon square space algorithm. So remarkably, for the special case of f2, so it turns out this is not optimal. One can beat this bound for all values of k. But specifically for f2, you can go from root n actually down to log n over epsilon square. This is again going to be related to something we've talked in the past. And so now let me give you the AMS 99 sketch for F2. So this is the squared length of F. So what you're trying to estimate is the squared length of a vector. This vector you see through a streaming mechanism. So implicitly, each like stream increment or decrement is a linear update to the vector F. And what you want is a squared length. Now let's use Johnson-Lindenstrauss. So Johnson-Lindenstrauss says you can project F to essentially, and if you go through the math, essentially to 1 over epsilon squared dimensions and the length is preserved up to a 1 plus epsilon factor, 1 plus minus epsilon factor. So what the AMS 99 sketch does is basically simulate a Johnson-Lindenstrauss transform. Now what is JL? Let's again recall. So remember, so F one can think of just as a vector in R to the n. JL is basically going to multiply this with the matrix, where this is n. This, which is the number of rows, we can think of as 1 over epsilon squared. So now let me tell you exactly how this is going to work. Let's just think of just what happens with a single row, of this. I'm going to give you an algorithm which will not be a small space algorithm, and then we'll discuss how AMS make it into a small space algorithm. So let's start with something really basic. So let's store a random Gaussian vector G in Rn. So each coordinate of G is drawn from a normal, and the update on seeing an element or pair in the stream just update the dot product F dot G. So formally, if you saw the element J comma C, you can think of this as adding a vector where the jth coordinate is C and all the other coordinates are 0. So think of this as a vector. So, and if you think of what G is just a collection of random Gaussians. So the update we can think of as x is equal to x plus C times G of J. Right? This is going to be, for that Gaussian, you're looking at the jth coordinate, and you just add that. This is the update. The output is simply x squared, which is just the dot product squared. Now recall that f dot g is a Gaussian of mean 0 and variance being the 2 norm of the length. And therefore, what you're outputting is exactly the variance. The expectation of the output is the variance. Right? So this is the AMS sketch. Any questions about that? Any questions? So this would be one sketch. This would be equivalent to outputting one coordinate here. You could repeat this a bunch of independent times, you get a bunch of coordinates, and then you can do various ways of trying to combine them. You can actually just output the length of everything. So what I described gives you one coordinate, but you could then output sort of the sums of squares of all the coordinates. Okay, and that's basically doing a JL transformation. Now, of course, there's a huge problem here that storing G requires n space. Right? I mean, it's an n-dimensional vector. It's an n-dimensional vector of independent Gaussians. So the solution is we don't need full independence. So one has to look through the math a little bit, but 4-wise independence suffices. And in some sense, we don't really need Gaussians, at least asymptotically. We just need, what we need is just that the expectation of G of I is 0 and the expectation of G of I is 1. That is, we just need random variables whose expectation is 0, whose variance is 1, I should say well behaved. Random variables. And it turns out that you might as well just use it's even easier. You could just use -1 +1 random variables because these will have the right variance. And so the final solution, what you do is you basically, the algorithm, instead of storing a random Gaussian vector, will instead choose a hash function that is 4-wise independent. So it's just going to map things to ±1, and then you have exactly the same algorithm. And the analysis is a little, one has to sort of dig through the math, but essentially at this point it should be relatively straightforward given what I've told you. You can write out the expressions for the expectations of the estimate. Now the expectation of the estimate is really the variance of the dot product. And the variance of the output is essentially the fourth moment of the dot, or is related to the fourth moment of the dot product. And because you get the fourth moment, you use 4-wise independence, and that's all you need. And so this essentially gives you a log n over epsilon squared algorithm. So I've gone through this sort of quickly. There are technical details here to be handled. But the way to really think about this is it's Johnson-Linden-Strauss. You're doing a low-dimensional projection. And you start off by saying, well, suppose I just use Gaussians, then all the approximation in the math goes through. Now, because I cannot afford to store Gaussians, instead you're going to store a more convenient random variable, a ±1, a Rademacher random variable. And moreover, you're also going to keep, it's going to be 4-wise independent. So this is really going to keep things simple. And so that's basically my sort of quick description of AMS. It's important that you see this at some point because it's sort of a classic result in streaming. But with this, I'm going to end the discussion on streaming, and I've covered what I think are three of the most fundamental problems. So counting distinct elements, finding heavy hitters, and frequency moment estimation. And at this, we'll move on to some other topics. So at this point, I'll stop the recording and I'll take any questions.